Okay, welcome. Here is another problem which is quite a cool problem. The physics is very easy to understand, and the mathematics is the only part which could be a little bit of a hiccup. So I'd like to give you guys a bit of an understanding or a roadmap on how to approach this problem. So yeah, we have an archerfish which intends to hit a insect which is sitting on a twig. The line of sight, when a fish looks at the insect with direct line of sight, uh, it will locate the fish, or it finds that the fish is located at a distance of 0.9 meters away at an angle of inclination, that is an angle of 36 degrees Celsius. Sorry, degrees. 36 degrees, not Celsius. So that's the angle of inclination that the fish must maintain in order to keep sight of, to keep the insect in sight. So over here I have kind of captured this now with a bit of input. So our fish is located at what I have designated as the origin, and the purple angle represents the angle that the fish will observe the insect at. The fish would like to hit the target, but we know that if it were to launch the water or squirt the water at the same angle, angle phi, we know that obviously due to gravitational effects, we know that the water won't make it to the insect. So the fish must launch the water at an angle different from the one given here, phi. And we have been instructed to give that an angle, launch angle, and name theta 0. Another thing that we have to take into account is the input, that the fish would like to hit the insect when the droplet is at the peak of its parabolic path. So basically, max height. So basically the droplet should not hit the insect on its way up, neither on its way down. So in other words, it shouldn't hit it on its way up, neither on its way down. That is, maybe let me draw it like that. We want it to hit it, we want the water to hit the insect exactly as the droplet reaches its max height. And we know what condition dictates to us whether we've reached the max height or not. Okay, here's one key observation. If the water squirted by the fish is to hit the insect, they must have the same position at the same time. Otherwise, it would not be in the same, it would not hit the water would not hit the insect. It's critical that the final position of the droplet be the same as the position of the insect. Well, here we're given this distance, this direct distance from the fish to the insect. So we could determine these coordinates xf and yf. And these coordinates are exactly given by xf is this d cosine of phi, and yf is given by d sine of phi. And these are the final positions that the final position which the droplet has to acquire. Okay, and what does this look like from the droplet's perspective, from the droplet that's intended to hit the insect? Well, this means the displacement of the droplet has to be v0x times t plus half ax t squared. But then we know that the droplet, once it's squirted by the fish, nothing propels it to speed up in the x direction. So we could safely discard this term. Basically, the ax is going to be 0. So what we have left is v0x times t, which we can write as the speed, the initial speed, times cosine of our angle of launch. Remember, our angle of launch is not phi, that is That was the angle of inclination which the fish needs to attain in order to observe the insect. But now what we're interested in here is the angle of launch, and that's the theta 0. So we're going to have cosine of theta 0 multiplied by t. And the analysis on the other end of the other direction, the other dimension, this is delta y. This is going to be v0y t plus half a y t squared. And this could be further written as v0 sine theta 0. Again, here, this is the angle of launch, sine theta 0, plus half a y t squared. Okay, while this is enough to get the water to hit the fish, the water to hit the twig, it's not fulfilling the conditions that were given to us. The other condition is that the water is to hit the insect at the top of its parabolic path. So then we need to find out when does this water reach the top of its path. And of course that max height condition is signified by the fact that the y component of the velocity becomes 0, which tells us that v0 y plus ayt must be 0. And from here we learn that t is going to be v0y minus over ay. And obviously the v0y here is nothing more than the speed. Maybe let's clean that up a little. It's nothing more than v0 sine theta 0 over ay. Don't worry about the negative here, because we know that based on our coordinate system, ay is going to be minus 9.8, so the negatives are going to cancel out. We're not working with negative time. We're not antiparticles. So now you have everything you need. You could simply substitute this t over there and also over there. And basically you could eliminate the v0, and you should be able to find what theta 0 is. This please don't be discouraged by the mathematical involvement, but carry out the mathematics as honest as you possibly can, and you'll realize that what the angle theta 0 is. If you have more questions or you'd like to see the full working out of this, let me know. Alrighty.